Time does not pass the same way for everyone. It feels constant because it moves with you, matching pace so precisely that deviation seems impossible. Clocks tick, days cycle, seasons turn. From the inside of a single life, time appears universal, absolute, and shared. Yet when two clocks are separated, one carried into motion, one left behind, they quietly disagree. Not because either is broken, not because measurements fail, but because time itself does not flow the same way everywhere. Astronauts returning from orbit age slightly less than the people they left behind. GPS satellites must correct their clocks dozens of times per day, or navigation fails within minutes. Time runs faster on mountaintops than at sea level, not metaphorically, but measurably, by billionths of a second that accumulate into certainty. Welcome to Sleep Knowledge. If you find comfort in exploring how the familiar becomes strange under examination, settle in and let time's quiet flexibility unfold slowly. And if you feel moved too, share where you are drifting off tonight. It is always warming to know how far these gentle explorations travel. Tonight, we'll explore why time refuses to be universal. Not to make existence feel unstable, but to understand why clocks disagree, why motion stretches duration, and how something that feels so absolute can be so deeply personal. And perhaps, by the end, why time's flexibility makes the universe more reliable, not less. Time feels like a river carrying everything forward at the same pace. It does not appear negotiable. Schedules align because everyone experiences the same hours, the same minutes, the same steady progression from past through present toward future. Meetings begin at agreed times. Trains arrive when expected. Ages accumulate in predictable ways. This shared experience is so fundamental that questioning it feels unnecessary. Time is simply there, moving, ticking, proceeding. It does not ask permission. It does not pause. It appears external to everything, a backdrop against which events unfold, but which remains unchanged by them. From the earliest age, the brain learns to treat time as stable. Day follows night. Hunger returns in cycles. Growth accumulates slowly but steadily. The mind builds its model of reality around this constancy, treating time as one of the few things that can be trusted absolutely. Cultures across history have reinforced this view. The sun rises at measurable intervals. Moon phases repeat. Seasons cycle. These rhythms feel cosmic, built into the fabric of existence itself. Time does not care about individual perspective. It does not bend to circumstance. It simply is. For most of human history, this intuition went unquestioned. Time was treated as a universal clock, ticking the same way everywhere, for everyone, without variation. Isaac Newton formalized this view in the 17th century, describing time as absolute, flowing uniformly without relation to anything external. His mathematics worked beautifully for planetary motion, falling objects, and everything within the reach of human experience. There was no reason to suspect otherwise. Every experiment confirmed it. Every observation aligned. Time was constant, and that constancy was not just convenient, it seemed fundamental to how reality operated. But constancy and universality are not the same thing. Constancy means time flows steadily from the perspective of any single observer. Universality means time flows the same way for all observers simultaneously. The first turns out to be true. The second does not. The difference remained hidden for centuries because everyday motion is slow. Walking speed, horse speed, even the speed of sound, all are tiny fractions of the speed that makes time's flexibility visible. At human scales, time behaves so close to universal that the deviation is invisible without extraordinarily precise instruments. It was only when physicists began studying light in the late 19th century that cracks in the universal time model began to appear. Light does something strange. It moves at the same speed for every observer, regardless of how fast that observer is moving. This should not be possible if time is universal. If someone runs toward a beam of light and someone else stands still, intuition says the running person should measure a faster light speed. The same way a person running toward a thrown ball sees it approach faster than someone standing still. But light does not behave this way. It always moves at exactly 299,792,458 meters per second, no matter who measures it or how they are moving. This fact, confirmed by experiment after experiment, created a problem. Speed is distance divided by time. If light's speed is always the same, but observers are moving differently, then either distance must change, or time must change, or both. Albert Einstein, working through this problem in 1905, realized that both do change. Distances contract along the direction of motion, and time itself stretches or compresses depending on relative motion. This is not an illusion. It is not a trick of perception. It is how time actually behaves. When two observers move relative to each other, each sees the other's clock running slow. Not because the clocks are malfunctioning, but because time genuinely passes at different rates. The faster the relative motion, the greater the difference. At walking speed, the effect is so small that it would take millions of years to accumulate a single second of difference. But at speeds approaching the speed of light, the effect becomes dramatic. This discovery rewrote physics. Time was no longer a fixed stage. It became something flexible, responsive, tied to motion in ways that defied intuition. And here's where the strangeness begins. Each observer is correct from their own perspective. There is no single true. Time that applies everywhere is personal. Not in a metaphorical sense, but in a measurable, physical sense. Every observer carries their own version of now, and these versions do not line up perfectly when motion is involved. This is called time dilation. The word dilation means stretching or expanding. Moving clocks dilate time; they experience duration more slowly relative to stationary clocks. The mathematics describing this are precise. The predictions are testable, and the results have been confirmed thousands of times across more than a century of experimentation. So far, we've seen how time feels universal because it moves with each observer. But there's something stranger still. Motion does not just affect time, it creates time. Consider a photon, a particle of light. From the photon's perspective, if such a perspective could exist, the journey from emission to absorption takes no time at all. 0 seconds. A photon, emitted by a distant star billions of light years away and absorbed by a human retina, experiences no duration between those two events. This is not metaphor. It is the direct consequence of traveling at the speed of light. At that speed, time dilation becomes infinite. Time stops. For anything moving slower than light, time passes, but the rate depends entirely on speed. The closer to light speed, the slower time moves relative to a stationary observer. Which raises a question. If time slows down when you move fast, what happens at the speed of light itself? The answer is not what most people expect. At the speed of light, time stops entirely. Not metaphorically, measurably. A photon experiences no duration between when it is emitted and when it is absorbed. From its frame of reference, the entire journey is instantaneous. This creates a profound asymmetry. For the stationary observer, the photon takes billions of years to arrive. For the photon, the trip takes no time at all. Both perspectives are correct. Neither is more true than the other. This asymmetry is not a problem to be solved. It is a feature of how reality operates. Time is not a universal clock that all things experience the same way. It is a local phenomenon tied to motion, responsive to speed. The universe does not enforce a single timeline. It allows each observer to carry their own. The clearest demonstration of time dilation comes from particles called muons. Muons are created when cosmic rays, high-energy particles from space, strike Earth's upper atmosphere. They are unstable, decaying into other particles in about 2.2 microseconds when measured at rest in a laboratory. A microsecond is 1/1,000,000th of a second. 2.2 microseconds is not much time. Even traveling at nearly the speed of light, a muon should only be able to travel about 660 meters before decaying. The upper atmosphere is roughly 15,000 meters above sea level. By simple calculation, muons created high in the atmosphere should never reach the ground. They should decay long before arriving. Yet they do reach the ground. Detectors measure them constantly. This is because, from the muon's perspective, time is moving more slowly. The muon is traveling so fast, about 99.8%, the speed of light, that time dilation extends its lifespan. From Earth's perspective, the muon lives much longer than 2.2 microseconds. From the muon's perspective, time passes normally, but the distance it needs to travel contracts. Both perspectives yield the same result. The muon reaches the ground. Time dilation and length contraction work together, making the impossible possible. This experiment has been repeated countless times since the 1940s. The results never vary. Muons arrive. Time dilation is not theory. It is measurement. And here's where it connects to daily life. GPS satellites orbit Earth at about 20,000 kilometers above the surface, traveling at roughly 14,000 kilometers per hour. At that speed, time dilation is small but measurable. The satellite clocks run slower than clocks on the ground by about 7 microseconds per day due to their motion. 7 microseconds does not sound like much, but GPS works by measuring the time it takes radio signals to travel from satellites to receivers. Light moves at about 300 meters per microsecond. A timing error of 7 microseconds translates to a position error of about 2,100 meters. Without correcting for time dilation, GPS would accumulate errors of more than 2 kilometers per day. Within a week, navigation would be useless. This is not just abstract. Every GPS satellite carries an atomic clock corrected for time dilation 18 times per day. Without those corrections, location errors accumulate at 10 kilometers per day. The adjustments are automatic, invisible, built into the system. But they are there, quietly compensating for the fact that time does not pass the same way in orbit as it does on the ground. Time dilation is not a curiosity. It is engineering. Motion affects time, but motion is not the only factor. Gravity also affects time, and in some ways this effect is even stranger. In 1915, Einstein extended his work on time and motion to include gravity. What emerged was general relativity, a theory that describes gravity not as a force pulling objects together, but as a curvature of spacetime itself. In this view, massive objects like Earth do not pull things toward them. Instead, they warp the fabric of space and time, and objects move along the curves created by that warping. One consequence of this curvature is gravitational time dilation. The closer you are to a massive object, the slower time passes, relative to someone farther away. This sounds abstract, but it is measurable. Atomic clocks are sensitive enough to detect time differences caused by changes in altitude of less than a meter. A clock on the ground runs slower than a clock on a table. A clock at sea level runs slower than a clock on a mountaintop. The differences are tiny billionths of a second per day, but they are real, and they accumulate. In 1971, physicist Joseph Hafele and astronomer Richard Keating conducted an experiment that demonstrated both forms of time dilation simultaneously. They flew atomic clocks around the world on commercial airplanes, then compared them to clocks that had remained on the ground. The flying clocks were affected by two opposing factors. Their motion caused them to run slower due to velocity-based time dilation, but their altitude caused them to run faster due to gravitational time dilation. When the clocks were compared after the flights, the measured differences matched Einstein's predictions to within experimental error. The eastbound clocks, which moved with Earth's rotation and therefore travelled faster, lost time. The westbound clocks, which moved against Earth's rotation and therefore travelled slower, gained time. This experiment has been repeated with increasing precision. Every result confirms the same conclusion. Time is not absolute. It is shaped by motion and gravity. GPS satellites experience both effects. Their motion slows their clocks by about 7 microseconds per day. But their altitude being farther from Earth's gravitational field speeds their clocks up by about 45 microseconds per day. The net effect is that satellite clocks run faster than ground clocks by about 38 microseconds per day. This offset is built into the system. Without it, GPS would drift out of alignment almost immediately. Navigation depends on time dilation being real, measurable, and predictable. Now that motion's role and gravity's role are clear, the deeper question emerges. What does it mean for time to be personal? Personal time does not mean arbitrary. It means relational. Every observer has a valid perspective, and those perspectives connect through precise mathematical relationships. When two observers move relative to each other, each sees the other's clock running slow. This sounds like a contradiction, but it is not. The key is that now is not the same for both observers. From one observer's perspective, an event happens now. From another observer's perspective, moving relative to the first, that same event might be slightly in the past or slightly in the future. The order of events can even reverse if the events are far enough apart and the motion is fast enough. This does not create logical problems because causality is preserved. Events that can influence each other. Events connected by cause and effect always maintain their order for all observers. Only events that are too far apart to influence each other can appear in different orders to different observers. The universe does not allow paradoxes. It simply allows different perspectives to be equally valid. This raises something called the twin paradox. Imagine two twins, one who stays on Earth and one who travels into space at high speed, then returns. Because the traveling twin moves fast, time dilation means less time passes for them than for the twin who stays behind. When the traveling twin returns, they are younger. Not by perception, but measurably, biologically. This has been tested with atomic clocks on airplanes and satellites. It works. The traveling clock ages less. The paradox arises from symmetry. If motion is relative, shouldn't each twin see the other's clock running slow? How can one twin end up younger? The resolution lies in acceleration. The traveling twin must accelerate to leave, decelerate to stop, accelerate to return, and decelerate to land. Acceleration breaks the symmetry. The twin who accelerates is the one who ages less. There is no paradox, only asymmetry. And asymmetry is not a flaw. It is information. This is not just theory. Twin paradox experiments have been performed with atomic clocks on airplanes. The results match predictions to the nanosecond. Time dilation is not speculation. It is measurement. Astronauts on the International Space Station experience time dilation every day. The station orbits at about 28,000 kilometers per hour. Astronauts who spend 6 months in orbit age about 0.007 seconds less than people on the ground. 7 thousandths of a second is not noticeable, but it is real. Astronauts return fractionally younger than they would have been had they stayed on Earth. This effect would become more pronounced with faster travel. A spacecraft traveling at 90% the speed of light for 1 year would experience only about 5 months of time, while 10 years would pass on Earth. At 99% the speed of light, 1 year of travel would correspond to 7 years passing on Earth. At 99.9%, it would be 22 years. The mathematics are precise, the effects are measurable, and the implications are profound. Time is not a river carrying everything at the same pace. It is a landscape, and different paths through it take different durations. This connects to something we touched on earlier. If time is personal, what does now mean? The answer is that now is local. Every observer has a present moment, but those moments do not align globally. Events that are simultaneous for one observer may not be simultaneous for another. This does not create chaos because causality remains intact. Events that can affect each other maintain their order. Events that are too far apart to interact can appear in any order without consequence. The universe does not require a universal present moment to function. It only requires consistency within causal chains. And here's where intuition quietly fails. Gravity does not pull on time. It is time. In general relativity, spacetime is a single unified fabric. Space and time are not separate. They are aspects of the same structure. Massive objects curve this fabric, and that curvature is what we experience as gravity. When Earth curves spacetime, it curves both space and time. The spatial curvature makes objects fall. The temporal curvature makes time pass more slowly near the surface. These effects are inseparable. Gravity is not something acting on spacetime. Gravity is the curvature of spacetime. This means time near a massive object is fundamentally different from time far away. Not just measured differently, but different in structure. Black holes demonstrate this extreme. Near the event horizon of a black hole, gravitational time dilation becomes so extreme that time nearly stops relative to a distant observer. An object falling toward a black hole would appear to slow down, freeze, and fade from view as it approached the horizon. From the falling object's perspective, time passes normally. It crosses the horizon without noticing anything unusual at that moment. But from outside, the crossing appears to take infinite time. Both perspectives are correct. Both describe the same reality. They simply describe it from different positions in curved spacetime. The universe allows this. It does not demand that all perspectives agree on timing. It only demands that they remain consistent with each other through precise mathematical relationships. Remember the question we started with. Why do clocks disagree? We're closer to an answer now. Clocks disagree because time is not external to reality. It is part of reality, and reality does not enforce uniformity. It enforces relationships. Each clock measures duration accurately from its own perspective, but perspectives differ when motion or gravity separates them. The disagreement is not error. It is information about the structure of spacetime itself. This realization reshapes what time is. Time is not a backdrop against which events occur. Time is woven into events themselves. It does not exist independently. It arises from relationships between objects, motion, and gravity. Physicists sometimes say that time is what clocks measure. This sounds circular, but it captures something important. Time is not a thing that exists prior to measurement. It is what emerges from the process of measuring intervals between events. Without change, without motion, without events unfolding, the concept of time would be meaningless. Time is not separate from the universe. It is how the universe organizes itself. This is where the universe refuses to simplify. Time does not exist independently of events. Events do not exist independently of time. They create each other. What becomes visible here is that time dilation is not a distortion of something pure. It is the natural behavior of time when examined carefully. The intuition that time flows universally is not wrong in a moral sense. It is limited. It works beautifully at human scales, where motion is slow and gravity is weak. But it breaks down when motion approaches light speed or gravity becomes strong. This does not make reality unreliable. It makes it richer. Time is still measurable. Clocks still work. Predictions still hold. The only thing that changes is the realization that each observer carries their own version of duration, and these versions connect through relativity rather than universality. Living with this knowledge does not require abandoning everyday intuition. At walking speed, time behaves close enough to universal that the difference does not matter. Schedules align, meetings happen, ages accumulate predictably. But beneath that practical uniformity lies flexibility. Time adjusts. It responds. It bends with motion and curves with gravity. This bending is not a flaw. It is precision. The universe does not approximate time. It allows time to vary exactly as much as relativity requires. And that precision is what makes technology like GPS possible. The system works because engineers understand time dilation. They account for it. They build corrections into satellite clocks. Without understanding that time is flexible, GPS would fail. With that understanding, navigation is accurate to within meters. This is one of those areas where science does not just describe the world, it enables interaction with it. Time dilation moves from abstract concept to practical tool. Another way to see this is through particle accelerators. Machines like the Large Hadron Collider accelerate particles to 99.9999% the speed of light. At that speed, time dilation extends particle lifespans by thousands of times. Particles that would normally decay in nanoseconds survive long enough to travel meters, even kilometers, before decaying. This allows physicists to study them. Without time dilation, many experiments would be impossible. The universe is not hiding time dilation. It is displaying it constantly. Every high-energy cosmic ray, every GPS satellite, every atomic clock measurement. Time dilation is not an edge case. It is fundamental behavior, visible whenever motion or gravity becomes significant. So where does this leave understanding? Time is not what it appears to be from a single, slow-moving perspective. It is more flexible, more relational, more tied to the structure of spacetime than everyday experience suggests. But flexibility does not mean arbitrariness. Time still follows rules. Those rules are precise. They are testable. They are confirmed by every experiment designed to measure them. The universe does not offer a universal clock, but it offers something better. It offers consistency. Every observer's measurements are valid. Every clock's duration is accurate from its own perspective. And those perspectives connect through relativity in ways that allow predictions, technology, and navigation to work precisely. Time's flexibility does not undermine reliability. It deepens it. Living with this understanding means accepting that time is not external to experience. It is part of experience. Each observer moves through their own duration, and those durations differ when motion or gravity separates them. This does not make existence chaotic. It makes it structured. The structure is just more intricate than intuition suggests. There is comfort in this. The universe does not demand that time be simple. It only demands that it be consistent. And consistency is exactly what relativity provides. Time dilation is not a problem to be solved. It is a feature to be understood. And understanding it does not require abandoning the sense that time flows. It only requires recognizing that the flow is personal, not universal. The experience of time dilation becomes more vivid when imagining extreme scenarios. Consider a spacecraft accelerating to very high speeds. From the perspective of people on Earth, the spacecraft's journey takes years, perhaps decades. But for the travelers aboard, time passes more slowly. At 90% the speed of light, a round trip to a nearby star system that takes 20 years from Earth's perspective would feel like only 9 years to the travelers. They would return having aged 9 years while their friends and family aged 20. This is not science fiction. It is the direct consequence of special relativity. The mathematics are straightforward. The predictions are testable in principle, though interstellar travel remains beyond current capability. But the principle has been tested at smaller scales countless times. Every particle accelerator, every GPS satellite, every cosmic ray muon reaching the ground. Time dilation works exactly as predicted. The universe does not approximate these effects. It delivers them with precision. Consider another example, closer to everyday experience. Commercial airliners fly at about 900 kilometers per hour. At that speed, time dilation is extraordinarily small, but still present. A flight attendant who spends their career flying accumulates a time difference compared to someone who remains on the ground. Over 30 years of flying, the difference amounts to roughly 1/100th of a second. This is far too small to notice biologically, but it is measurable with atomic clocks, and it follows precisely from the mathematics of special relativity. The fact that everyday motion produces such tiny effects explains why time dilation was not discovered earlier. Human experience operates at speeds where the effect is negligible. Only when technology advanced enough to measure billionths of a second did time dilation become observable. But once observed, it proved consistent. Every experiment designed to test it confirmed the predictions. Every technology built on those predictions worked. Time dilation moved from theoretical curiosity to established fact through accumulated measurement. Another way this becomes visible is through particle physics. Particles called pions decay very quickly when at rest, about 26 nanoseconds on average. But when accelerated to high speeds in particle accelerators, their lifespans extend dramatically. At 99.9% the speed of light, a pion lives about 40 times longer than it would at rest. This extension is not metaphorical. It is measured directly. Detectors count how far pions travel before decaying, and the distance matches time dilation predictions exactly. Without time dilation, these particles would decay before traveling measurable distances. With it, they travel meters, sometimes tens of meters, allowing physicists to study their properties. Entire branches of physics depend on time dilation being real and predictable. The same principle applies to cosmic phenomena. Cosmic rays are particles that travel through space at nearly the speed of light. Some are protons. Some are heavier nuclei. When they strike Earth's atmosphere, they create cascades of secondary particles. Many of these secondary particles would decay long before reaching the ground if time passed at the same rate for them as it does for stationary observers. But time dilation extends their lifespans just enough for them to reach sea level. Detectors measure these particles constantly. Their arrival is direct evidence that time dilation operates at cosmic scales. The universe is full of natural experiments demonstrating time dilation. It does not hide the effect. It displays it continuously. This connects back to why GPS requires corrections. The system depends on precise timing. Radio signals from satellites travel at the speed of light, and receivers calculate position by measuring how long those signals take to arrive. If satellite clocks ran at the same rate as ground clocks, the system would work. But they do not. Motion slows them by about 7 microseconds per day. Altitude speeds them up by about 45 microseconds per day. The net effect is 38 microseconds per day faster. Without correction, this difference would accumulate. Within a day, position errors would exceed 10 kilometers. Within a week, GPS would be unusable. Engineers correct for this by adjusting the frequency of satellite clocks before launch. The clocks are built to run slightly slower than ground clocks, so that once in orbit, time dilation brings them into alignment. This adjustment is permanent. It is built into the hardware, and it works because time dilation is consistent and predictable. The system demonstrates something remarkable. Time dilation is not a limitation to be overcome. It is a feature to be understood and incorporated. Once understood, it becomes a tool. The flexibility of time also appears in gravitational contexts, beyond simple altitude differences. Neutron stars, for example, are extraordinarily dense objects left behind after massive stars collapse. A neutron star might have twice the mass of the Sun compressed into a sphere, only 20 kilometers across. Gravity near a neutron star's surface is intense, is less than ℏ0. 5 is greater than time dilation. There is significant. A clock on the surface of a neutron star would run about 30% slower than a clock far away in space. This is not speculation. It is calculation based on general relativity, and those calculations match observations of neutron star behavior. If a signal were sent from the surface of a neutron star, its frequency would be shifted toward the red end of the spectrum due to gravitational time dilation. This redshift has been measured. It matches predictions. The universe does not approximate these effects. It delivers them precisely. Black holes represent the extreme case. Near a black hole's event horizon, time dilation approaches infinity. An outside observer watching an object fall toward the horizon would see it slow down asymptotically, never quite reaching the boundary. From the falling object's perspective, it crosses the horizon in finite time. No dramatic event marks the crossing from the object's point of view. But from outside, the crossing appears to take forever. Both perspectives are valid. Both describe the same physical process. They simply describe it from different positions in curved spacetime. This asymmetry is not a problem. It is structure. It reveals how spacetime behaves near extreme gravity. Observatories have detected gravitational waves ripples in spacetime from merging black holes. The signals match predictions from general relativity with extraordinary precision. This agreement extends to time dilation effects near the event horizons. The universe does not deviate from relativity's predictions. It follows them exactly. What time dilation reveals ultimately is that spacetime has structure. That structure is not fixed or absolute. It responds to mass, energy, and motion. Time is part of that structure. It bends, stretches, and adjusts according to precise mathematical relationships. This responsiveness is not a flaw. It is the nature of space-time itself. And that nature is what makes the universe consistent across all scales. The question of whether time is real often arises when time dilation is discussed. If time is flexible, if it varies with motion and gravity, does it truly exist? The answer depends on what real means. If real means universal, unchanging, and absolute, then time is not real in that sense. But if real means measurable, consistent, and predictive, then time is profoundly real. Time is not a substance. It is not made of anything. It is a relationship between events. And relationships can be as real as objects. Temperature is a relationship between molecules. It is not a thing, yet it is measurable, predictive, and real. Time is similar. It is what emerges when events are ordered and intervals are measured. Without events, time would be meaningless. But with events, time becomes the structure that organizes them. This understanding shifts how questions about time are framed. Instead of asking, "What is time?" physics asks, "How does time behave?" And the behavior is consistent, measurable, and predictive. Time behaves differently depending on motion. It behaves differently depending on gravity, but it always behaves according to the same underlying principles. Those principles are captured in Einstein's field equations, a set of mathematical relationships that describe how matter and energy curve spacetime. The equations are complex, but their predictions are clear. And every prediction tested so far has been confirmed. Gravitational waves provide one of the most dramatic confirmations. When massive objects like black holes orbit each other, they create ripples in spacetime that propagate outward at the speed of light. These waves carry energy and information about the events that created them. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, detected the first gravitational wave signal in 2015. The signal came from two black holes merging more than 1 billion light-years away. The detected waveform matched theoretical predictions with stunning precision. Not only did it confirm that gravitational waves exist, but it also confirmed the behavior of spacetime near merging black holes. Time dilation plays a role in these events. Near the black holes, time passes more slowly than it does far from them. This affects the frequency of the gravitational waves. The observed frequencies match what general relativity predicts when time dilation is included. Since that first detection, LIGO and other observatories have detected dozens more gravitational wave signals. Each one confirms the same underlying physics. Spacetime curves. Time dilates. Gravity propagates at the speed of light. The universe operates exactly as general relativity describes. Another experimental confirmation comes from observing binary pulsars. Pulsars are rapidly rotating neutron stars that emit beams of radiation. When a pulsar is part of a binary system, two stars orbiting each other, the orbital motion affects the timing of the pulses. Time dilation causes the pulsar's clock to run slower when it moves faster in its orbit. This creates a periodic variation in pulse timing that can be measured with extraordinary precision. Astronomers have observed several binary pulsar systems over decades. The timing variations match general relativity's predictions perfectly. The agreement extends to many decimal places. In one famous system, called PSRB 1913+16, the orbital decay caused by gravitational wave emission has been measured for more than 40 years. The decay rate matches theoretical predictions to better than 1%. This level of agreement is not accidental. It is the result of reality following the same mathematical relationships that relativity describes. Time dilation is not an approximation. It is exact behavior. The precision of these measurements matters not just for confirming theory, but for understanding what precision means. Reality does not round numbers. It does not approximate. It operates according to relationships that hold with perfect consistency. Time dilation is one of those relationships. It connects motion, gravity, and duration through mathematics that never fail when tested. This precision is what allows technology to function. GPS satellites depend on time dilation corrections being exactly right. Off by even a small percentage, and navigation degrades rapidly. The fact that GPS works flawlessly is ongoing confirmation that time dilation operates as described. Millions of people use GPS every day without thinking about relativity. But relativity is there, built into the system, quietly compensating for the fact that time passes differently in orbit. Technology becomes a form of continuous experimentation. Every GPS receiver, every satellite uplink, every navigation calculation, all of them test relativity millions of times per day. and relativity continues to pass every test. This connects to something deeper about scientific understanding. Theories are not proven in the sense of becoming absolutely certain. They are confirmed through accumulated testing. Each successful prediction increases confidence. Each failed prediction would force revision. General relativity has been tested for more than a century. It has passed every test designed to probe its predictions. Time dilation, as one of its key features, has been confirmed in contexts ranging from atomic clocks on airplanes to gravitational waves from distant black holes. The theory could still be incomplete. It might require modification at extremely small scales, where quantum effects become important. But within its domain motion, gravity, and the structure of spacetime, it remains unchallenged. Time dilation is not speculative. It is established behavior. Living with this knowledge means recognizing that time is more intricate than intuition suggests. But intricate does not mean unreliable. Time follows rules. Those rules are consistent, and consistency is what matters. Another dimension of time dilation involves the cosmological scale. The universe is expanding. Space itself stretches, carrying galaxies farther apart. This expansion affects how time is experienced across cosmic distances. Light traveling from distant galaxies is redshifted, its wavelength stretched by the expansion of space. This redshift includes a time component. Events occurring in distant galaxies appear to unfold more slowly when observed from Earth. This is not exactly time dilation in the special relativity sense, but it is related. The expansion of space creates a relationship between time and distance that affects how events are observed. Distant supernovae, for example, appear to brighten and fade more slowly than nearby ones. This is not because distant supernovae behave differently. It is because the expansion of space stretches the time intervals between photons reaching Earth. Cosmologists account for this when analyzing distant events. The corrections are precise. The observations match expectations when expansion is included. Time on cosmological scales is not universal. It is woven into the expansion of space itself. The universe does not enforce a single timeline that all galaxies follow. It allows each region to carry its own local time, with those local times connected through the geometry of expanding spacetime. This might sound abstract, but it has observable consequences. The cosmic microwave background, the afterglow of the Big Bang, carries information about time in the early universe. The temperature variations in this radiation reveal density fluctuations from when the universe was about 380,000 years old. Those fluctuations froze into the radiation at a specific moment in cosmic time. But cosmic time is defined by averaging over all the different local times across space. The fact that this average can be meaningfully defined and that it produces consistent results shows that time's flexibility does not create chaos. It creates structure. The universe is not a random collection of times. It is an organized network of local times that connect through geometry. And that organization is what makes cosmology possible. From this perspective, time dilation is not an obstacle to understanding. It is a tool. By measuring how time behaves in different contexts, near massive objects, at high speeds, across cosmic distances, physicists learn about the structure of spacetime itself. Time becomes a probe for exploring reality. This reverses the usual relationship between time and measurement. Normally, time is the backdrop against which measurements occur. But in relativity, time is part of what is being measured. Atomic clocks measure duration with such precision that they reveal spacetime's geometry. GPS satellites map Earth's gravitational field through timing differences. Gravitational wave detectors measure spacetime ripples by tracking how light travel time changes. Time is not just being measured. it is revealing structure, and the structure is remarkably consistent. At every scale tested, from laboratory experiments to cosmological observations, time behaves as general relativity predicts. There are no anomalies, no unexplained deviations, no regions where the theory breaks down within its domain. This consistency is one of the most striking features of modern physics. The same equations that describe time dilation for an airplane also describe it for a gravitational wave from merging black holes. Scale does not change the principles. It only changes the magnitude of the effects. Time dilation operates everywhere. It is not confined to exotic situations. It is fundamental behavior that becomes visible only when instruments are sensitive enough to measure it. Every clock is experiencing time dilation relative to other clocks that are moving differently or sitting in different gravitational fields. The effect is usually tiny, but it is always there. This universality is worth reflecting on. Time dilation is not a special phenomenon that occurs only in extreme conditions. It is the normal behavior of time, made visible through precise measurement. The intuition that time flows uniformly is not wrong at human scales. It is a useful approximation. But approximation and exactness are different things. Physics seeks exactness, and when examined exactly, time reveals flexibility. This flexibility does not undermine the reliability of reality. It deepens it. The universe does not approximate its behavior. It operates according to relationships that hold with precision across all tested scales. Time dilation is one of those relationships. And understanding it means recognizing that time is part of the geometry of the universe itself. This view of time has implications beyond physics. It suggests that change is more fundamental than persistence. The universe is not a static thing unfolding in time. The universe is change, and time is how that change is structured. If time is relational rather than absolute, then now becomes something different than intuition suggests. The present moment is not a universal instant that all observers share. It is local. Each observer has their own present, and those presents do not align perfectly when motion or gravity separates them. This creates a view of reality that is sometimes called the block universe. In this view, past, present, and future all exist in a four-dimensional structure. What changes is not reality itself, but which slice of that structure each observer identifies as now. This does not mean the future is predetermined. It means that the distinction between past, present, and future is not built into the universe, it is built into observers. From a photon's perspective, there is no duration between emission and absorption. The entire journey is instantaneous. From a stationary observer's perspective, the photon takes time to travel. Both are correct. Neither is more fundamental. This suggests that reality is richer than any single perspective can capture. The universe does not have a preferred viewpoint. It accommodates all viewpoints simultaneously, connecting them through geometry. Time, in this framework, is not something flowing through the universe. It is a dimension of the universe, woven together with space into a single fabric. Events do not happen in time. They are located in space-time, with temporal coordinates just as real as spatial ones. This might sound abstract, but it has concrete consequences. It explains why causality is preserved even when observers disagree about timing. It explains why light speed is constant for all observers. It explains why time dilation and length contraction work together to maintain consistency. The block universe view does not eliminate time. It contextualizes it. Time remains real, measurable, and meaningful. It simply is not universal in the way everyday experience suggests. Some find this view unsettling. If all moments exist equally in spacetime, Does choice matter? Does change matter? The answer is that choice and change are woven into the structure. Each observer moves through space-time along their world line, a path that traces their motion through both space and time. The experience of making choices, of time flowing, of events unfolding, is real. It simply is not accompanied by a universal now that all observers share. This does not diminish experience. It situates it. Each observer's experience is valid from their perspective, and all perspectives connect through the geometry of space-time. Another way to think about this involves simultaneity. In Newtonian physics, two events are simultaneous if they happen at the same time. This seems obvious, but at the same time requires a universal time that all observers agree on. Special relativity shows that no such universal time exists. Events that are simultaneous for one observer may not be simultaneous for another if the observers are moving relative to each other. This is not a failure of measurement. It is genuine relativity. Simultaneity depends on the observer's state of motion. For events that are far apart and have no causal connection, different observers can disagree about which happened first. This disagreement is not a problem because events that cannot influence each other do not need to have a definite order. Only events that are connected by cause and effect maintain their order for all observers. This preservation of causality is built into the structure of spacetime. Light cones provide a useful way to visualize this. Every event has a past light cone, the set of events that could have influenced it, and a future light cone, the set of events it could influence. Events inside the light cones are causally connected and maintain their temporal order for all observers. Events outside the light cones are not causally connected and can appear in different orders to different observers. This structure preserves causality while allowing simultaneity to be relative. The universe is consistent, but consistency does not require uniformity. What becomes visible here is how carefully the universe maintains logical coherence. Time can be flexible. Simultaneity can be relative. Order can depend on perspective. But causality, the ability of events to influence each other, remains absolute. This is not accidental. It is mathematical necessity. The same equations that allow time dilation also preserve causality. Relativity does not create paradoxes. It prevents them. Consider the twin paradox again, but in more detail. Two twins. One stays on Earth. One travels at high speed to a distant star and returns. The traveling twin experiences less time and ages less. This seems paradoxical because motion is relative. From the traveling twin's perspective, Earth moved away and returned. Shouldn't the Earth twin age less from that perspective? The resolution is that the situations are not symmetric. The traveling twin accelerates. The Earth twin does not. Acceleration breaks the symmetry. During the acceleration phases leaving Earth turning around, returning the traveling twin is not in an inertial frame. Special relativity applies to inertial frames, where objects move at constant velocity. Acceleration requires general relativity, which includes gravity and non-inertial motion. During acceleration, the traveling twin's perspective on simultaneity shifts. What they consider now on Earth jumps forward. This shift accumulates more time for Earth than for themselves. The result is that the traveling twin ages less, and both twins agree on this when reunited. There is no paradox. There is asymmetry created by acceleration. This has been tested with atomic clocks. Clocks flown around the world on airplanes, which experience acceleration during takeoff, flight maneuvers, and landing, show less elapsed time than clocks that remained on the ground. The measured differences match predictions from both special and general relativity. The twin paradox is not hypothetical. It is observable. Astronauts experience it. Particles in accelerators experience it. Satellites experience it. The universe does not approximate these effects. It delivers them exactly. Understanding the twin paradox requires recognizing that motion and rest are not symmetric when acceleration is involved. The twin who accelerates is the one whose clock runs slow. There is no ambiguity once acceleration is accounted for. This connects to a broader principle. Physics is local. What matters is what happens in an observer's immediate vicinity, their local spacetime. Distant events do not directly affect local measurements, but local measurements are influenced by the geometry of spacetime, which is shaped by distant masses and motion. This locality is what allows relativity to avoid paradoxes. Observers can disagree about distant events without creating logical contradictions, because those disagreements cannot produce conflicting local outcomes. Causality travels at the speed of light. No information can propagate faster. This speed limit ensures that causal relationships remain consistent for all observers. Time dilation, length contraction, and the relativity of simultaneity all work together to maintain this consistency. They are not separate effects. They are different aspects of the same underlying geometry. Spacetime is not divided into space plus time. It is a single unified structure where separation in time affects separation in space, and vice versa. Motion through space affects motion through time. Moving faster through space means moving slower through time. The total motion through spacetime, measured as the spacetime interval, remains constant. This is why light, which moves through space at maximum speed, does not move through time at all from its own perspective. All its motion is through space, leaving none for time. Slower objects divide their motion between space and time. A stationary object moves through time at maximum rate because it is not moving through space. This trade-off is not metaphorical. It is geometric. The space-time interval between events is invariant. All observers agree on it, even if they disagree on the separate space and time components. This invariance is what makes relativity work. It provides a foundation that all observers share, even as their individual measurements of space and time differ. From this perspective, time dilation is not time behaving strangely. It is time behaving consistently within the geometry of space-time. The strangeness arises from expecting time to be independent of motion and gravity. Once that expectation is released, time's behavior becomes natural, perhaps not intuitive, but natural. Nature does not require intuition to operate. It simply operates. And when measured carefully, its operation follows precise mathematical relationships. Time dilation is one of those relationships. It is not an approximation or a correction. It is fundamental behavior made visible through measurement. The philosophical implications extend beyond physics. If time is personal rather than universal, then experience itself is localized in a way that might not be obvious. Each observer's experience of duration is accurate from their perspective, but those durations do not align globally. There is no master timeline that all experiences fit into. This does not create solipsism. All observers remain connected through space-time geometry. Their differing experiences of duration relate to each other through precise mathematics. But it does suggest that reality is not arranged around a single temporal perspective. The universe does not have a now. It has many local nows, all valid, all connected, none privileged. Some find this liberating. If there is no universal present, then the pressure to synchronize perfectly with an external timeline dissolves. Each observer moves through space-time at their own pace, and that pace is correct for them. Others find it disorienting. If time is personal, what anchors experience? What provides continuity? The answer is that continuity comes from causality, not from universal time. Events influence other events in sequence. That sequence defines personal history, and personal histories connect through the structure of space-time. The universe does not demand synchronization. It demands coherence. And coherence is what relativity provides. Time remains ordered. Causes precede effects. Duration accumulates. What changes is the recognition that this ordering is local, not global. And local ordering is enough. It is enough to maintain causality, enough to allow physics to be predictive, enough to support the complexity of reality. The universe does not require universal time to function. It functions through local time and geometric relationships. This realization shifts how time is understood. It is not a container that events occupy. It is a dimension that events are structured within. And that structure is remarkably flexible while remaining perfectly consistent. This connects to one of the deeper mysteries in physics. Why does time have a direction? In the equations of relativity, time can run forward or backward with equal validity. Yet experience clearly shows a direction. The past is fixed. The future is open. Events unfold in a sequence that does not reverse. This asymmetry is called the arrow of time. It does not come from relativity. It comes from thermodynamics. Thermodynamics describes how systems evolve toward higher entropy, greater disorder. Entropy always increases in closed systems. This increase defines a direction. The past is the direction of lower entropy. The future is the direction of higher entropy. Time dilation does not change this direction. It only changes the rate at which it is experienced. A moving clock ages more slowly, but it still ages forward. The universe does not reverse. It only varies in how fast different observers move through the same overall progression. This asymmetry between past and future is another feature that feels obvious, yet resists simple explanation. Relativity makes time flexible. Thermodynamics gives it direction. Together, they describe a universe that is both structured and dynamic. Time is not a prison. It is not a constraint. It is the medium through which change occurs. And change, however slow or fast, is what allows complexity to emerge. Without time, there would be no causality. No before and after. No sequence. No evolution. Time's flexibility does not erase these features. It enriches them by making duration personal while keeping structure universal. The historical development of understanding time reveals how difficult it was to move beyond intuition. For centuries, absolute time seemed so obviously correct that questioning it appeared unnecessary. Isaac Newton's Principia, published in 1687, formalized this view. Newton wrote that absolute, true, and mathematical time flows uniformly without relation to anything external. This description matched all available evidence. It worked beautifully for planetary motion, projectiles, pendulums, everything within the reach of 17th century science. But Newton's definition contained an assumption. It assumed that time could be separated from the events occurring within it. That time was a backdrop, independent and unchanging. This assumption went unquestioned for more than 200 years. Not because scientists were incurious, but because every experiment confirmed it. Clocks synchronized perfectly when compared. Events that appeared simultaneous to one observer appeared simultaneous to all observers. Motion did not affect duration in any measurable way. The limits of measurement technology hid time dilation's effect. Mechanical clocks were simply not precise enough to detect microsecond differences. Motion at human speeds, even the fastest trains or ships, produced time dilation effects, far below measurement thresholds. It was only when physicists began studying light that cracks appeared. Light's speed became a focal point of research in the 19th century. Experiments by Hippolyte Fizeau, Léon Foucault, and others measured light speed with increasing precision. What emerged was puzzling. Light appeared to move at the same speed regardless of the observer's motion. This contradicted expectations from Newtonian mechanics, where speeds should add together. The Michelson-Morley experiment in 1887 provided crucial evidence. Albert Michelson and Edward Morley attempted to measure Earth's motion through the hypothetical luminiferous ether, the medium that light was thought to propagate through. They expected to detect differences in light speed depending on Earth's direction of motion. They found none. Light moved at the same speed in all directions. This null result was repeated multiple times. It was not experimental error. It was real behavior that defied explanation within Newtonian physics. Several physicists proposed solutions. Hendrik Lorentz and George Fitzgerald suggested that objects contract along their direction of motion by just enough to make light speed appear constant. This was mathematically correct, but lacked physical justification. Albert Einstein in 1905 approached the problem differently. Rather than treating light speed constancy as something requiring explanation, he took it as a fundamental postulate. Light speed is constant for all observers, always. From this postulate, combined with the principle that the laws of physics are the same in all inertial frames, special relativity emerged. Einstein showed that if light speed is constant, then time and space must be flexible. Moving clocks run slow. Moving objects contract. Simultaneity is relative. These were not separate phenomena requiring separate explanations. They were different manifestations of spacetime's geometry. The mathematics were clear. The predictions were precise. But experimental confirmation took time. Early tests focused on light bending and gravitational redshift, which came from general relativity. Time dilation specifically was harder to test because it required precise clocks and controlled motion. The development of atomic clocks in the mid-20th century changed this. Atomic clocks measure time by counting oscillations in atoms, typically cesium or rubidium. These oscillations are extraordinarily regular. Modern atomic clocks are accurate to about 1 second in 30 million years. With such precision, time dilation became directly measurable. The Hafele-Keating experiment in 1971 used atomic clocks on commercial flights. The clocks were flown eastward and westward around the world, then compared to clocks that remained stationary. The flying clocks showed measurable differences. Eastbound clocks lost time. Westbound clocks gained time. The magnitudes matched Einstein's predictions within experimental uncertainty. This experiment has been refined many times since. Every iteration confirms the same result. Time dilation is real, measurable, and exactly as predicted. Particle physics provided another avenue for testing. In the 1940s and 50s, physicists studied cosmic ray muons. These particles are created high in the atmosphere when cosmic rays strike air molecules. Muons decay quickly, about 2.2 microseconds when at rest. At that rate, even traveling near light speed, they should decay before reaching sea level. Yet ground-level detectors measure muons constantly. Time dilation extends their lifespans just enough for them to reach the surface. This was not a single experiment, but an ongoing observation. Cosmic ray muons became a natural laboratory for testing time dilation. The effect was too large to attribute to measurement error or chance. Particle accelerators reinforced this. Accelerators like Fermilab and CERN routinely accelerate particles to very high speeds. The particles' lifespans extend exactly as time dilation predicts. Without accounting for time dilation, accelerator operations would fail. Particles would decay before traveling measurable distances. Experiments depend on time dilation being real and predictable. The Large Hadron Collider accelerates protons to 99.999999991% the speed of light. At that speed, time dilation is dramatic. From the proton's perspective, they circle the 27-kilometer ring in about 90 microseconds. From the laboratory perspective, each orbit takes about 90 microseconds times a factor of more than 7,000 due to time dilation. The mathematics are verified with every beam circulation. Millions of protons, billions of orbits, all confirming that time behaves exactly as special relativity describes. GPS satellites provided yet another test, one that operates continuously. GPS works by timing radio signals. Satellites broadcast their position and the exact time the signal was sent. Receivers compare signals from multiple satellites to calculate position. The system requires nanosecond precision. Without accounting for time dilation, GPS would accumulate errors of kilometers per day. Engineers building GPS in the 1970s and 80s initially debated whether relativistic corrections were necessary. Some argued the effects would be too small to matter. Others insisted on including them. The disagreement was resolved by testing. Early satellites were launched with adjustable clock rates, so corrections could be added or removed. When corrections were turned off, positioning errors grew rapidly. When turned back on, accuracy returned. There was no longer any doubt. Relativity was not optional. It was essential. Modern GPS satellites have relativity corrections built into their hardware. The clocks are manufactured to run at a slightly different rate, so that once in orbit, time dilation brings them into sync with ground clocks. Every GPS calculation is a test of relativity. Every navigation success is confirmation. Billions of GPS uses occur daily. Smartphones, aircraft, ships, surveying equipment, delivery trucks, all depend on time dilation corrections being exactly right. GPS is perhaps the most widespread practical application of general relativity. It takes an abstract concept, curved spacetime, and turns it into functional technology that millions use without thinking about physics. This transformation from theory to application demonstrates something important about scientific understanding. Theories are not merely descriptions. When accurate, they become tools. General relativity is not just a model of how gravity works. It is the foundation for technologies that depend on precise timing across different gravitational potentials. Beyond GPS, relativity influences other technologies. Telecommunications satellites must account for time dilation. Deep space missions use relativistic corrections when calculating trajectories. Gravitational wave detectors like LIGO incorporate space-time geometry into their fundamental design. Even technologies not explicitly built around relativity are constrained by it. The speed of light limit affects data transmission rates. Particle accelerators must account for relativistic mass increase. Atomic clocks used for global time standards measure durations that include gravitational time dilation. Technology has become a continuous test of relativity. Every device that depends on precise timing, high speeds, or strong gravitational fields operates in a relativistic context. And every one works. This is not coincidence. It is confirmation that relativity describes reality accurately. The accumulated evidence spans scales from subatomic particles to orbiting satellites to merging black holes. At every scale, the predictions hold. At every precision level, the measurements agree. Time dilation is not a hypothesis awaiting confirmation. It is established physics, tested thousands of times across more than a century. This level of confirmation matters. It means time dilation can be relied upon. Engineers can build systems assuming it works. Scientists can design experiments knowing the corrections will be accurate. Reliability does not require perfect understanding. The mathematics work even when intuition struggles. Predictions hold even when visualization fails. The universe does not demand comprehension. It simply behaves consistently. And consistency is what allows technology, measurement, and understanding to advance. From this perspective, time dilation is not mysterious. It is less than #0. 5 is greater than Vive. It is well-characterized behavior that follows precise rules. The mystery, if any remains, is not in time's behavior, but in why intuition expected something different. And that expectation traces back to evolutionary history. Human brains evolved in a world of slow motion and weak gravity. Under those conditions, time appears universal because the deviations are too small to notice. Intuition built on this experience naturally assumes universality. But universal and approximately universal are different. At human scales, time is approximately universal. At cosmic scales or high speeds, the approximation breaks down. This does not make intuition wrong. It makes it limited. Intuition provides a useful guide for everyday experience, but cannot be extended arbitrarily beyond that domain. Science exists partly to correct for intuition's limits. It provides tools, mathematics, measurement, experimentation that reveal behavior outside intuition's range. Time dilation is one of those revelations. It shows that reality is more flexible than intuition suggests, but also more structured. The flexibility is not arbitrary. It follows rules. And those rules are testable, predictive, and consistent. Living with this understanding means accepting that some aspects of reality require tools beyond intuition. Not because those aspects are irrational, but because they operate at scales where intuition was never calibrated. This acceptance does not diminish understanding. It expands it. By recognizing intuition's limits, understanding can grow beyond them. Time dilation remains counterintuitive. But counterintuitive and false are not the same. Many well-established features of reality contradict intuition while remaining thoroughly verified by measurement. Quantum mechanics is counterintuitive. Evolution is counterintuitive. The vastness of cosmic scales is counterintuitive. Yet all are supported by overwhelming evidence. Intuition is a starting point, not a final arbiter. It guides everyday experience effectively, but must defer to measurement when the two conflict. And in the case of time dilation, measurement speaks clearly. Time does not pass uniformly. It varies with motion and gravity in precisely predictable ways. This variation is not error. It is structure. The structure of spacetime itself. From this perspective, time dilation is not a distortion. It is time revealing its true nature. The intuition that time flows uniformly is not wrong. It is incomplete. Time does flow, but it flows at different rates for different observers, and those rates depend on motion and gravity. Understanding this does not mean visualizing curved spacetime or imagining four-dimensional geometry. It means accepting that time is relational. Each observer measures their own duration accurately, and those durations connect through precise mathematical relationships. The universe remains stable throughout this. Physics works. Predictions hold. Technology functions. Satellites orbit correctly. Clocks sync when corrected for dilation. Particle accelerators produce expected results. Time's flexibility does not undermine the reliability of reality. It supports it. This is worth noticing. A universe where time is flexible is not a universe where anything can happen. It is a universe where specific things happen in specific ways, and those ways are consistent enough to predict, measure, and use. Time dilation is not evidence of chaos. It is evidence of structure. As this exploration settles, a broader picture becomes visible. Time does not pass the same way for everyone, but it passes consistently for everyone, according to rules that connect all perspectives. The flexibility of time is not a flaw. It is precision. The universe does not enforce uniformity. It enforces relationships. Clocks disagree when separated by motion or gravity, but the disagreement is predictable, measurable, and meaningful. It tells us something about the structure of space-time itself. Astronauts age more slowly in orbit, not by much, but measurably. GPS satellites run faster than ground clocks, not dramatically, but enough to matter. Muons reach the ground because time stretches for them, not arbitrarily, but exactly as relativity predicts. Time is personal, but personal does not mean arbitrary. It means local, accurate, and connected through relationships that hold across all observers. Living with this knowledge does not require abandoning everyday experience. Schedules still work, ages still accumulate, days still cycle. But beneath that practical uniformity lies something deeper. Time is not a backdrop. It is a participant. It bends, stretches, and responds to the motion and gravity that shape the universe. And that responsiveness is what makes the universe reliable. Without time dilation, relativity would fail. With it, light speed remains constant, causality is preserved, and the universe remains consistent across all scales. The universe does not demand that time be simple. It only demands that time be consistent. And consistency is what relativity delivers. There is no urgency to resolve this fully. Time will continue behaving as it does, whether it is understood or not. Clocks will disagree when separated. Astronauts will age slowly in orbit. GPS will require corrections. The universe is patient with incomplete understanding. It allows partial knowledge to be functional. And partial knowledge, grounded in measurement and tested by experiment, is often enough. Time dilation does not ask to be visualized. It asks to be measured. And when measured, it reveals a universe that is flexible, structured, and profoundly consistent. From the beginning, time felt constant, universal, shared. Along the way, that constancy softened. What seemed absolute revealed itself to be relational. Yet nothing about time itself changed. It continued passing, ticking, organizing events. Current research continues exploring time's nature at frontiers where relativity and quantum mechanics intersect. General relativity describes time at large scales, planets, stars, black holes. Quantum mechanics describes behavior at small scales, atoms, particles, fields. The two theories are both extraordinarily successful within their domains, but they describe time differently. General relativity treats time as a dimension of space-time that curves and bends. Quantum mechanics treats time as an external parameter against which quantum states evolve. This difference creates tension. When physicists attempt to combine the theories into quantum gravity, time becomes problematic. One approach, called loop quantum gravity, suggests that space-time itself might be quantized, made of discrete chunks rather than being continuous. If correct, this would mean time is not infinitely divisible. There would be a smallest possible duration, perhaps around 10, -43 seconds, the Planck time. Another approach, string theory, treats particles as vibrations of tiny strings in higher dimensional spacetime. In some formulations, time emerges from more fundamental entities rather than being fundamental itself. These remain theoretical explorations. No experiment has yet probed the scales where quantum gravity effects would become important. But the question matters because it asks whether time is fundamental or emergent. If time is emergent, if it arises from something deeper, then time dilation would be a consequence of underlying processes rather than a fundamental feature. The equations would still work. The predictions would still hold, but the interpretation would shift. Currently, this remains open. Time might be fundamental, woven into the fabric of reality from the start, or it might emerge from quantum processes in ways not yet understood. Either way, time dilation remains valid. It is measured behavior that any complete theory must reproduce. Another active area involves black hole physics. Black holes create extreme time dilation. Near the event horizon, time slows dramatically relative to distant observers. But black holes also raise questions about information. Quantum mechanics suggests information cannot be destroyed, yet black holes appear to destroy information by swallowing it. This tension, called the black hole information paradox, remains unresolved. It involves both quantum mechanics and general relativity, making it a testing ground for quantum gravity theories. Time plays a central role. From outside, objects falling into a black hole appear to freeze at the horizon. Time dilation becomes so extreme that the crossing appears to take infinite time. But from the falling object's perspective, time continues normally. It crosses the horizon in finite proper time. How these perspectives reconcile with quantum information preservation remains unclear. Multiple proposals exist, but none has achieved consensus. This is where current research operates at the boundary of known physics, where new insights about time might emerge. Cosmology also probes time's nature. The universe's expansion creates a cosmological time, a way to label when events occurred relative to the Big Bang. But this cosmic time is not universal in the relativistic sense. It is an average over all the local times throughout space. Different regions of space, if they had different histories of expansion or gravity, would have different relationships to cosmic time. The early universe, shortly after the Big Bang, involved conditions far beyond current experimental reach. Temperatures, densities, and energies were extreme. Understanding time's behavior in those conditions requires theories that successfully merge general relativity and quantum mechanics. Currently, no such theory is fully developed. But progress continues, and every advance in understanding gravity, quantum fields, or cosmology constrains what time can be at fundamental levels. Time might be more flexible than even relativity suggests. Or it might have structure at small scales that relativity does not capture. The answers await better theories and more sensitive experiments. What remains consistent across all these explorations is that time is measurable, predictable, and structured. Whether fundamental or emergent, time exhibits behavior that follows mathematical relationships. Those relationships allow physics to function. They allow technology to operate. They allow understanding to deepen. And they allow the universe to remain coherent even when different observers experience different durations. For everyday life, these frontier questions matter little. GPS works. Clocks sync. Causality holds. Time dilation corrections are well understood and routinely applied. But the frontier questions shape how reality is conceptualized. They ask whether the features of reality we measure, directly time, space, matter, are the deepest level, or whether something more fundamental underlies them. Physics has encountered this pattern before. Temperature seemed fundamental until statistical mechanics revealed it as average molecular motion. Light seemed like a wave until quantum mechanics revealed photons. Space and time seemed separate until relativity unified them into spacetime. Each time, what appeared fundamental turned out to be emergent from something deeper. Time might follow this pattern, or it might not. The question remains open. And open questions are not problems. They are invitations. Physics advances by following those invitations carefully, testing ideas against measurement, refining theories until they match observation. Time dilation emerged from this process. It was not assumed. It was discovered by taking seriously the constancy of light speed and working through the implications. Future discoveries about time will emerge the same way from careful attention to what experiments reveal and willingness to revise assumptions when evidence demands it. This process requires patience. Questions about time's ultimate nature might not be answered quickly. They involve scales far beyond current experimental reach. But patience has served physics well. General relativity was proposed in 1915. Gravitational waves were predicted immediately. That they were not detected until 2015, a century later. The delay was not because the theory was wrong. It was because the technology needed to detect gravitational waves took a century to develop. Similarly, understanding time at quantum gravity scales might require technologies not yet invented and mathematics not yet developed. The universe is patient with incomplete understanding. It continues functioning while science catches up. Time dilation will keep affecting satellites. Muons will keep reaching the ground. Black holes will keep warping spacetime. All independent of whether humans understand the deepest nature of time. This is part of what makes science different from other forms of knowledge. It does not require complete understanding to be useful. Partial understanding, when accurate within its domain, is enough to make predictions and build technology. General relativity might be replaced by a more complete theory someday. But that theory will have to reproduce all of general relativity's successes within its domain. Time dilation will remain an established feature that any successor theory must explain. This is how scientific progress works. New theories extend understanding but do not invalidate what worked before. They explain why earlier theories worked and where their limits lie. Newtonian mechanics was not wrong. It is accurate at low speeds and weak gravity. Relativity extends to high speeds and strong gravity. Both are correct within their domains. Future theories will likely extend beyond relativity without contradicting it. Time dilation will remain valid within relativity's domain even if deeper explanations emerge. This layered structure of understanding is one of science's strengths. Each layer is reliable within its context. Deeper layers provide broader context without invalidating shallower ones. Time dilation belongs to the relativistic layer. It is well tested, thoroughly confirmed, and routinely applied. Whatever lies beneath quantum gravity, emergent spacetime, or something not yet imagined, must reproduce time dilation's predictions. So time dilation is not provisional. It is established. The only question is how it fits into a deeper understanding. And that question does not undermine current knowledge. It enriches it by suggesting connections to other aspects of physics not yet fully understood. Living with incomplete knowledge is natural. No one understands everything about anything. Science advances by recognizing what is known reliably and what remains uncertain. Time dilation falls in the known category. Its behavior is measured, its predictions are confirmed, its applications are widespread. The deeper questions about time's ultimate nature fall in the uncertain category. They are active research areas where physicists continue exploring. Both categories coexist without conflict. Understanding can be reliable without being complete, and reliability is what matters for technology, prediction, and practical application. Time dilation demonstrates this clearly. It is reliable enough to base global navigation systems on, reliable enough to design particle accelerators around, reliable enough to predict black hole mergers. That reliability does not require knowing whether time is fundamental or emergent. It requires knowing how time behaves under various conditions. And that is well established. The universe does not demand deep metaphysical understanding before allowing technology to function. It simply requires accurate models of behavior. Relativity provides those models for time dilation. And those models work. Every time, without exception. This success is worth noticing. A theory proposed over a century ago, based on mathematics that seemed abstract and counterintuitive, now underpins technologies used by billions. GPS alone represents a vindication. It takes time dilation from theoretical prediction to daily utility. The fact that it works seamlessly is ongoing confirmation that relativity describes reality accurately. Millions of navigation calculations occur every second. Each one tests relativity. Each one confirms it. This is not dramatic. It is quiet, continuous, reliable. Which is precisely what makes it significant. Time dilation is not a curiosity. It is infrastructure. Modern life depends on it in ways most people never consider. And that dependence is justified. The theory has earned trust through accumulated evidence. It has passed every test. It has enabled every technology built on its principles. Time does not pass the same way for everyone. But it passes consistently for everyone, according to precise mathematical relationships. Those relationships are what make the universe reliable despite its flexibility. Clocks disagree, but their disagreement is predictable. Astronauts age slowly, but the rate is calculable. Satellites run fast, but corrections are known. Everywhere time dilation appears, it does so with precision. Not approximately, not roughly, exactly. This precision is what transforms abstract theory into functional technology. And functional technology is validation that the theory captures something true about reality. Time's flexibility is not disorder. It is structure. Measured structure that holds across all tested scales. From particle accelerators to GPS satellites to merging black holes, the same equations apply. The same predictions hold. The same behavior emerges. This universality of physical law is reassuring. The universe does not change its rules arbitrarily. It operates according to relationships that persist. Time dilation is one of those relationships. It persists across scales, contexts, and applications. And understanding it, even incompletely, reveals something profound. Reality is more flexible than intuition suggests, but more structured than randomness would allow. Time bends without breaking. It varies without becoming arbitrary. It remains measurable even when not universal. This balance flexibility with structure characterizes many aspects of physics. The universe allows variation while maintaining coherence. Time dilation exemplifies this. Duration varies between observers, but the variation follows rules. Those rules connect all observers through spacetime geometry. No observer is isolated. All connect through mathematics that describe their relationships precisely. This is perhaps the deepest lesson. Personal time does not mean isolated time. Each observer's measurements are valid from their perspective and relate to all other perspectives through consistent mathematics. The universe accommodates all viewpoints simultaneously. It does not privilege one perspective over another. It simply ensures they relate consistently. And consistency, maintained through geometry, is what makes reality reliable. Clocks still measure duration. Schedules still align. Ages still accumulate. The only thing that shifted is the realization that each observer carries their own version of now, and those versions connect through motion, gravity, and the curvature of spacetime. The implications of personal time extend into questions about consciousness and experience. If each observer has their own duration, what does this mean for subjective experience of time? Consciousness appears to operate with its own sense of timing. Time can seem to pass quickly when engaged, slowly when bored. Memory compresses some periods and expands others. Attention creates its own temporal structure. These subjective variations are not the same as time dilation. Time dilation is physical, measurable with clocks. Subjective time is psychological, measured by experience. But both point to the same underlying principle. Duration is not absolute. It depends on perspective. Physical time dilation depends on velocity and gravitational field. Subjective time dilation depends on neural processing and attention. The mechanisms differ entirely. Yet the conclusion is similar. There is no universal clock that all observers, physical or conscious, experience identically. This does not mean time is arbitrary. Both forms of time dilation follow rules. Physical time dilation follows relativistic equations. Subjective time follows patterns in neural activity. Both are structured. Neither is chaotic. The parallel is worth noting because it suggests that time's relationship to perspective is deep. Not just a feature of physics, but something fundamental about how reality organizes information. Observers, whether particles, satellites, or conscious minds, carry their own temporal perspective. And those perspectives connect through relationships, rather than through a universal, external time. This view treats time as informational. Time organizes sequences of events, establishing order without requiring absolute duration. In physics, this ordering is called causal structure. Events that can influence each other have a definite order. Events that cannot influence each other can appear in any order without consequence. The causal structure remains absolute even while duration and simultaneity become relative. This ensures consistency. The universe remains coherent because causality does not depend on universal time. In conscious experience, something similar might occur. The order of thoughts and perceptions creates personal narrative. That narrative has structure even when duration feels variable. Boredom stretches time. Engagement compresses it, but the sequence remains. Cause precedes effect in memory even when duration feels elastic. This suggests time serves primarily as ordering rather than as duration. Duration emerges from ordering through local clocks, atomic in physics, neural in consciousness. But ordering itself might be more fundamental than duration. This is speculative. The relationship between physical time and conscious experience remains poorly understood. But time dilation hints that reality organizes itself around relationships rather than absolutes. Each observer interacts with reality through their local perspective. Those perspectives differ when separated by motion, gravity, or neural state. But they connect through structure, physical equations for clocks, neural patterns for consciousness. Structure is what makes perspectives reconcilable. Without structure, different perspectives would produce contradictory accounts that could not coexist. But the universe does not permit contradictions. It permits differences that resolve through precise relationships. Time dilation is one of those differences. Clocks disagree, but their disagreement is exactly what relativity predicts. The disagreement itself contains information about motion and gravity. Similarly, subjective time varies, but the variation contains information about attention and neural processing. Both forms of variation are meaningful rather than random. Meaning emerges from structure. And structure is what both physics and consciousness provide to organize time. This does not mean physics and consciousness are the same. Physical time is measurable with instruments. Conscious time is accessible only through subjective report. But both suggest that time is relational rather than absolute. Both show duration depending on context. Both maintain order even when duration varies. These parallels are not coincidence. They reflect something about how information gets organized into temporal sequences. Physics has learned this through relativity. Neuroscience is learning it through studies of time perception. Both point toward time as a framework for ordering events rather than as an independent entity. In physics, this framework is spacetime. In consciousness, the framework is not yet fully characterized. But research continues, exploring how neural activity creates the experience of duration and sequence. One area of study involves how the brain predicts timing. The brain constantly generates predictions about when events will occur. These predictions shape perception. When predictions match reality, time feels normal. When predictions fail, time can feel distorted. This happens during surprising events. They often feel like they take longer than they actually did. The brain's temporal predictions are not perfect. They are calibrated by experience and updated through learning. But they create a sense of flow that organizes experience. Physical time dilation does not affect these predictions directly. A person experiencing time dilation would not notice it subjectively because their neural activity would proceed at the same rate relative to their local time. Astronauts in orbit do not feel time passing more slowly. Their experience is normal. It is only when they return and compare clocks that time dilation becomes visible. This separation between physical and experiential time is important. Time dilation affects physical processes, atomic clocks, particle decay, light propagation. But experience remains unchanged because neural processes are physical and therefore equally affected. An astronaut's neurons fire at the same rate relative to the astronaut's local time, whether in orbit or on the ground. The entire body, including the brain, ages more slowly in orbit, but the astronaut experiences time normally. This shows how deeply intertwined time is with physical processes. Experience emerges from those processes. So when time dilates, experience dilates proportionally. The astronaut does not notice time slowing because their perception slows equally. Everything remains synchronized within their frame of reference. Only external comparison reveals the difference. Only by comparing clocks or biological aging does time dilation become apparent. This highlights why time dilation remained hidden for so long. Within any single frame of reference, time appears normal. Deviation only becomes visible through comparison between frames. And comparison requires precise measurement. Before atomic clocks, such precision was unavailable. Time dilation existed, but was undetectable. Technology revealed it by enabling comparisons that were previously impossible. And once revealed, time dilation proved consistent across all measurements. This pattern-hidden behavior, revealed by improved measurement, appears throughout scientific history. Atomic structure was hidden until technology could probe small scales. Gravitational waves were hidden until detectors became sensitive enough. Time dilation was hidden until clocks became precise enough. Each time, the revealed behavior followed mathematical predictions. Reality did not surprise in arbitrary ways. It surprised in specific ways that equations had already described. This suggests that mathematics captures something genuine about reality. Not just approximate descriptions, but accurate representations of underlying structure. Time dilation's equations were written before the technology existed to measure it directly. Yet when measurement became possible, the equations proved correct. This is remarkable. It means theoretical physics can predict phenomena before they are observed. Not always. Physics has made wrong predictions too. But when predictions are correct as time dilations have been, they demonstrate that mathematics is not merely useful notation. It is a language that reality speaks. Time dilation speaks through equations that relate velocity, gravitational potential, and duration. These equations are not approximations. They are exact relationships that hold precisely. GPS proves this daily. The corrections are not rough estimates. They are calculated to nanosecond precision. And navigation works because the calculations are exact. This exactness is worth emphasizing. The universe does not tolerate approximation. It operates according to relationships that hold with perfect consistency. Time dilation is one of those relationships. It holds everywhere it has been tested. It holds to the limits of measurement precision. And those limits keep improving. Atomic clocks become more precise. Measurement techniques become more sensitive. Tests probe new regimes. Every improvement confirms time dilation. Every new test matches predictions. This accumulation of evidence is not just quantity, it is quality. Each test probes different aspects: motion, gravity, combination of both. Each confirms the same underlying mathematics. The consistency across different tests demonstrates that time dilation is not a narrow phenomenon limited to specific situations. It is general behavior that applies universally. This universality matters because it means time dilation cannot be explained away as artifact or approximation. It is how time actually behaves. Accepting this means accepting that intuition was incomplete. Time does not flow uniformly. It varies with motion and gravity. But this variation is not disorder. It is structure made visible. The structure of spacetime responding to mass, energy, and motion. Living with this understanding does not require constant awareness of relativity. Everyday experience remains valid within its domain. Time appears universal at human speeds and ordinary gravitational fields. But beneath that appearance lies flexibility. A flexibility that becomes visible when conditions change, when speeds increase, when gravity strengthens, when measurements become precise. Technology now operates in that regime. Satellites orbit fast enough and high enough that time dilation matters. Atomic clocks are precise enough that gravitational time dilation from altitude differences is measurable. As technology advances, more systems will need to account for time dilation. Future spacecraft traveling at higher speeds will experience greater effects. Future clocks with greater precision will detect smaller differences. Time dilation will become more relevant, not less, as capabilities increase. This suggests that relativity is not merely accurate, but increasingly necessary. The better technology becomes, the more it encounters regimes where relativity matters. GPS demonstrates this already. It is impossible to build a global positioning system that works without accounting for time dilation. The effects are too large to ignore. Future technologies will face similar requirements. Any system requiring nanosecond timing across altitude differences must account for gravitational time dilation. Any spacecraft traveling at significant fractions of light speed must account for velocity-based time dilation. Relativity will transition from theoretical physics to practical necessity for increasing numbers of applications. And each application will serve as ongoing test. Every technology that works confirms the theory it is built on. Time dilation is no longer just physics. It is infrastructure. It is engineering constraint. It is design requirement. This transformation from theory to practice demonstrates something important about scientific knowledge. When theories are accurate, they become useful. When useful, they become infrastructure. When infrastructure, they become invisible. Most people using GPS do not think about relativity. But relativity is there, built into the system, enabling the functionality taken for granted. This invisibility is success. Technology works so well that users do not need to understand the physics behind it. But the physics remains essential. Without it, the technology would fail. Time dilation exemplifies this. It is simultaneously theoretical concept and practical requirement, abstract and concrete, mathematical and measurable. This dual nature, theoretical yet practical, characterizes much of modern physics. Ideas that seem abstract prove essential for technology. Equations that appear removed from experience turn out to describe behavior precisely. Time dilation is not exceptional in this. It is representative. It shows how physics moves from speculation to confirmation to application. And application provides the strongest validation. Theories that work in practice are not merely convenient fictions. They capture something true about reality. Time dilation works. It works in particle accelerators. It works in satellites. It works in gravitational wave detections. This consistency across contexts demonstrates truth, not convenience. And truth, in physics, means accurate description of behavior that holds across all tested regimes. Time dilation meets that standard. It is not hypothesis. It is established feature of reality. Living with this knowledge means recognizing that time is more intricate than it appears. But intricacy is not fragility. The universe is reliable precisely because it follows consistent rules. Time dilation is one of those rules. And understanding it, even incompletely, reveals how carefully reality maintains coherence. This does not make existence unstable. It makes it precise. The precision of time dilation allows a deeper understanding of how reality maintains consistency across different frames of reference. Every observer measures events from their own perspective, yet those perspectives never produce logical contradictions. This coherence is not accidental. It is built into the geometry of spacetime. Imagine two events far apart in space. One observer, stationary, sees them occur simultaneously. Another observer, moving at high speed, sees one event occur before the other. This sounds like a contradiction. How can events be both simultaneous and sequential? The resolution lies in recognizing that simultaneity is not absolute. It depends on the observer's state of motion. Both observers are correct within their own frame of reference. The apparent contradiction dissolves when you realize there is no single, universal present moment that all observers must share. Each carries their own present, and those presents are related through the geometry of spacetime. This relativity of simultaneity is essential for preventing paradoxes. If simultaneity were absolute, then time dilation would create logical problems. But because simultaneity is relative, everything remains consistent. The universe does not choose one perspective as correct. It validates all perspectives and relates them mathematically. This egalitarian treatment of reference frames is called the principle of relativity. No inertial frame is privileged. all are equally valid. Time dilation follows from this principle, combined with light speed constancy. If all frames are equally valid and light speed is constant, then time and space must adjust to maintain consistency. The adjustments are not corrections to flawed measurements. They are genuine differences in how spacetime is experienced from different perspectives. And those differences connect through precise relationships that preserve causality and prevent contradictions. This is what makes relativity elegant. It does not add complexity arbitrarily. It reveals inherent structure that maintains coherence across all perspectives. Time dilation is one aspect of that structure. Length contraction is another. Relativity of simultaneity is another. All are different facets of how space-time geometry operates. None can be understood in isolation. They work together to maintain consistency. This interconnection means that accepting time dilation requires accepting the entire geometric framework of space-time. The phenomena are inseparable, but this is not a burden. It is clarity. One unified framework explains multiple phenomena that would otherwise appear unrelated. Before relativity, time dilation, length contraction, and light speed constancy would have seemed like separate mysteries. Relativity shows they are expressions of the same underlying geometry. This unification is characteristic of successful physical theories. They reveal that apparently diverse phenomena share common origins. Maxwell's equations unified electricity and magnetism. Quantum mechanics unified wave and particle behavior. Relativity unified space and time. Each unification simplified understanding by revealing deeper structure. Time dilation, viewed this way, is not an isolated oddity. It is part of how spacetime responds to motion and gravity. And spacetime's response is not arbitrary. It follows from fundamental symmetries and conservation laws. The mathematics of spacetime geometry encode these symmetries. The Einstein field equations relate spacetime curvature to mass and energy distribution. Solutions to these equations describe how time dilates near massive objects or at high velocities. The equations are complex. Solving them exactly is possible only in special cases: spherically symmetric masses, empty space, uniform expansion. But numerical solutions can be computed for more complex situations. Black hole mergers, neutron-star collisions, cosmological evolution. These numerical solutions match observations when precise data is available. Gravitational wave signals from merging black holes match simulated waveforms with extraordinary accuracy. The match is not approximate. It is precise enough to extract information about the masses, spins, and distances of the merging objects. This level of agreement demonstrates that general relativity's description of spacetime geometry is accurate even in extreme conditions. And time dilation is integral to that description. Near merging black holes, time runs at dramatically different rates at different distances. This affects the gravitational wave signals in specific ways. Detectors measure those signals. Theorists model them. The agreement confirms the theory. Each detection is another confirmation that time behaves as general relativity describes. The accumulated weight of evidence is overwhelming. Time dilation has been confirmed in particle accelerators, atomic clocks on airplanes, GPS satellites, binary pulsars, gravitational wave observations, and countless other contexts. No test has ever contradicted it. Every measurement matches predictions. This consistency across such diverse tests demonstrates that time dilation is not an artifact of specific measurement techniques or particular situations. It is fundamental behavior that appears everywhere motion or gravity creates differences between observers. The behavior is sometimes called gravitational redshift when referring to light. Light, climbing out of a gravitational field, loses energy, and its frequency decreases. It becomes redder. This redshift is directly related to gravitational time dilation. A clock deep in a gravitational field runs slower, so the light it emits has lower frequency. The effect has been measured in laboratory settings using Nussbauer spectroscopy, where gamma rays are sent up or down a tower only 20 meters tall. The gravitational time dilation over that small height difference is detectable. It has also been observed in white dwarf stars, whose strong gravity causes significant redshift in their spectral lines. The measured redshift matches predictions from general relativity. Even the Sun causes measurable gravitational redshift. Light emitted from the Sun's surface is slightly redshifted compared to light from the same atomic transition in a laboratory on Earth. The effect is small, only about 2 parts per million. But it is measurable and matches theoretical predictions exactly. These confirmations span enormous ranges in gravitational field strength. From laboratory experiments with Earth's gravity to observations of white dwarfs with gravity thousands of times stronger. All confirm the same relationship between gravity and time. The relationship is not metaphorical, it is quantitative. Given the gravitational field strength, time dilation can be calculated precisely. Given the time dilation, gravitational field strength can be inferred. This bidirectional relationship makes time dilation both a consequence and a probe. It reveals information about space-time geometry. Gravitational wave detectors use this principle. They measure tiny changes in light travel time caused by passing gravitational waves. Those changes reveal the wave's amplitude and frequency. From that information, physicists extract details about distant cosmic events, black hole masses, neutron star compositions, the expansion rate of the universe. Time dilation, combined with precise measurement, becomes a tool for studying the cosmos. This transformation from theoretical concept to observational tool represents science functioning at its best. Understanding enables measurement. Measurement refines understanding. The cycle continues. Time dilation is no longer just something to be understood. It is something to be used. And use validates understanding. Tools built on false principles do not function. GPS based on incorrect time dilation corrections would fail immediately. But GPS works. Gravitational wave detectors work. Particle accelerators work. All because time dilation is understood accurately. This success is not guaranteed. Physics could have been wrong. Predictions could have failed. Technology could have collapsed. But they did not. And the reason is that general relativity captures something true about space-time geometry. Time dilation is part of that truth. Not a convenient approximation. Not a mathematical artifact. But accurate description of how time actually behaves. Living with this knowledge means accepting that reality is more structured than intuition suggests. Time is not a simple backdrop. It is a dimension of space-time that responds to mass, energy, and motion. That responsiveness is not weakness. It is flexibility. And flexibility, when governed by precise relationships, creates a universe that is both varied and coherent. Time can pass at different rates for different observers. But those rates relate through mathematics that ensure consistency. Clocks can disagree. That their disagreement contains information about motion and gravity. Simultaneity can be relative, but causality remains absolute. These features work together. They form a coherent picture where flexibility and structure coexist. The universe does not choose between order and variation. It maintains both. Time dilation exemplifies this. It shows that time can vary while remaining measurable, predictable, and meaningful. and meaningful time is enough. It is enough to support causality, enough to enable technology, enough to organize experience. The universe does not require time to be universal. It requires time to be consistent. And consistency is exactly what general relativity provides. This does not make existence unstable. It makes it precise. Time dilation is not a distortion of something pure. It is the accurate behavior of time when motion and gravity are accounted for. The universe does not require time to be universal. It requires time to be consistent. And consistency is what relativity provides. Astronauts return younger. Not by years, but by fractions of seconds. GPS satellites correct their clocks constantly, not because they malfunction, but because time genuinely passes differently in orbit. Muons reach the ground, not because physics bends rules, but because time stretches exactly as predicted. In each case, time dilation is not an obstacle. It is information. Understanding time dilation does not mean visualizing four-dimensional spacetime or grasping curved geometry intuitively. It means recognizing that time is flexible, relational, and tied to motion and gravity. The flexibility is not chaos. It is structure. And that structure allows the universe to remain reliable, even when time does not pass the same way for everyone. There is comfort in this. The universe does not demand perfect understanding as a condition for functioning. It continues regardless. Time keeps organizing events. Clocks keep ticking. Motion keeps stretching duration. The mind can rest with partial understanding, not because full understanding is impossible, but because partial understanding is enough to recognize the pattern. Time is not external to reality. It is woven into reality. It arises from relationships between events, motion, and gravity. And those relationships hold with precision that allows predictions, technology, and navigation to function flawlessly. So time does not pass the same way for everyone, but it passes consistently. Each observer's duration is accurate from their perspective, and those perspectives connect through relativity. The universe is not waiting for time to be fully understood. It simply continues, organizing change, structuring events, allowing complexity to unfold. And in that continuation lies reassurance. Time's flexibility does not make the universe fragile. It makes it resilient. It allows motion without breaking causality. It allows gravity without erasing consistency. Time is personal, but the universe remains whole. And perhaps that is enough. Better sleep, a lighter day.